Okay, let's continue on by looking at a particular kind of work. There are lots of different kinds of work, but we're going to look at one particular kind today, and that is boundary work. Boundary work. Boundary work. W bound. Boundary work. So let's say we have a system, a gas or something, and this system is in a piston cylinder device. Okay, so here's our piston, and here's our gas. Could be anything. Could be a liquid, could be a solid. Hell, it could be a solid. Could be a two-phase mixture. Who knows? But let's say it's a gas. And this piston, under the influence of the gas, moves upward a certain distance. So we're going to move up a distance dx. So then we end up in a new position right here. So there's the piston, the old position, and then it moves up to a new position. All right? So our gas ends up looking like this now, okay? So our gas, there we go. Now this gas has a particular pressure, P, and notice this displacement, dx, is actually an infinitesimal displacement. Because it's infinitesimal, the pressure is approximately constant, okay? So the pressure is approximately constant during this infinitesimal process. Let's calculate the work that the gas does on the piston as the gas expands. Little bit of work, and that's the work done by the boundary of the system changing shape or volume. So the system has now changed shape and volume. And I want to calculate the boundary work associated with that. Well, the definition of work is force dot dx. Okay? Now, the pressure inside of the gas, inside of the piston cylinder device, is exerting a force on the bottom side of the piston. Okay? And what is that force equal to? Well, the piston has some kind of an area. Maybe it's a circular piston or something. Who knows? So this piston has some sort of an area. A piston. So this piston has some kind of area. So the force is equal to a pressure, which is a force per unit area, times the area of the piston. The force is the pressure of the gas times the area of the piston. That's the force on the piston due to the gas. The displacement, of course, dx, okay? And so the force is pointing in that direction, and so is dx, so they dot together, and you get pressure, area piston, dx. Okay, that's the differential or infinitesimal boundary work associated with the gas expanding over this differential or infinitesimal process. Now, this quantity right here, area piston times the displacement of the piston dx, that is the change in volume of the gas. This extra volume in here, that extra volume due to the upward displacement of the piston, is dx times the area of the piston. So this quantity here is d volume or dv. So the differential boundary work is equal to pressure times the change in volume of the system. So differential boundary work is equal to pressure times the change in volume of the system. Put a box around that. That's an important equation. So that is how you calculate, at least for a differential process, boundary work. Now, one other little thing. As the piston moves upward, the gas is doing work on the piston. It's pushing against the piston, and the gas is doing work. It's doing work against the piston. So this quantity here, PdV, is actually work done by the system. So I'm going to write here, note, by system. This work is being done by the system against the piston. If instead we were pressing down on the piston and moving it downwards, our dx would be negative. It would point in the opposite direction of the force, and we would end up with a negative term in here if we were doing work on the system. So this is positive. PDV is positive when the system does work, boundary work. When it expands and it has some pressure, it's doing boundary work. It's losing energy by doing work, okay? Now, let me show you how to eyeball the amount of work a system does over some process. What do I mean by eyeball? I mean graphically. Graphically. So let's say we have some system. Could be a piston cylinder device containing a gas. The gas could be the system. Who knows? So let's say we got a piston here with a gas inside. This is my system. My system is the gas. So this is state one. And then we end up with state two, where maybe the piston is moved upwards. So the gas is expanded. So this is state two. All right. Now, if I sketch the process on a pressure volume diagram, it might look something like this. Maybe this is state one here, and then I go over some path, and I end up at state two. These are the end states. State one, state two. We have a volume V1. I have a volume V2. And of course, I have a pressure P1 and I have a pressure P2. Okay. And then I take this path, as you can see here. What's the work? What's the boundary work over the process from state one to state two? Well, the boundary work, W bound from state one to state two, is the integral of the differential work from state one to state two. And that's equal to the integral of PDV. Pressure times the differential change in volume as I go from V1 to V2. So the boundary work over the process is the integral of PDV. How is that represented on this graph? This is zero pressure. Let's say this is zero right here. That integral, the integral of PDV, is indicated by the area underneath the pressure curve on the PV diagram. So this integral PDV is equal to the area under the curve. work bound equals integral PdV, the area under the pressure curve. So if somebody gives you the process on a PV diagram, you should be able to qualitatively determine the work. You should be able to qualitatively determine the work. Maybe we should do a few quick examples here. Let's say I have a system that goes from state 1 to state 2. I'll show you the path on a PV diagram, and we can determine which one involved more work being done by the system. So here's our system, some mass. We start off at state 1. And then we end up at state 2. Okay, I have a V1, a P1, bunch of stuff at state 1. And then I have a V2, P2, bunch of stuff at state 2. And I have the following process. PV. Let's see here. This is state 1. That's state 2. Let's say this is the process. Okay, that's the process 1 to 2. I'll put a bar on top of it. That's process 1 to 2 with a bar. What if I instead, so the work, the boundary work is given by the area under the curve. So this represents boundary work 1 to 2 bar. Okay, that's the boundary work, 1 to 2 bar. What about, let's take a different path. Let's take a different path. State 1, same state. State 2, same state. But instead we take the following path. Pressure goes to 0. Expands at 0 pressure, and then pressure shoots up to P2. I'm going to call that path 1 to 2 tilde. 1 to 2 tilde. What's the boundary work done by the system along this path? What's the area underneath the PV curve? 0. Work bound 1 to 2 tilde, 0. Along this process, it's non-zero. It's some positive value. There's positive area underneath the PV curve. Here, no work is being done because pressure goes to 0 during the expansion process. Okay? This is why work is a path function. It depends not on the end state, but on the path taken during the process. Okay? Not just on the end state, it is path dependent as well. If it's path dependent, if work is path dependent, it is a path function. Okay? Now let's do a little example here.